Okay, hello everyone. Let's go ahead and take a look at the ratio test. Again, we are trying to determine whether or not an infinite series converges or diverges. Now the ratio test is going to be very useful for us because it's going to help us determine if a series is absolutely convergent or not. Now let's just jump into the form of the ratio test, and it says this. It says if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Now just take a look at what that looks like. It's going to be very, very nice and easy and convenient for us to use the ratio test to test for absolute convergence, because we don't have to search for another series. We only need to take the series that was actually given to us and use the nth plus 1 term divided by the nth term, and then determine whether or not it is less than 1, greater than 1, or equal to 1. And notice that we have the absolute value here so that we can test for absolute convergence. So if it's less than 1, then the infinite series is absolutely convergent. If it is greater than 1, it's divergent. If it is equal to 1, then the ratio test is inconclusive. And we need to use other means to go ahead and determine whether or not that particular infinite series is convergent or divergent. Now, let's take a look at an example where the infinite series is absolutely convergent. So remember that our ratio test should produce a value that is less than 1. So here we have an infinite series, 2 to the n plus 5 divided by 3 to the n. And notice again, I'm just taking the nth plus 1th term and multiplying it by the reciprocal of the a sub nth term. And then I can go ahead and take a look at all kinds of cancellations if I can. So notice that I got the 2 to the n plus 1 plus 5. Notice the 3 to the n and the 3 to the n plus 1 are only going to differ by a factor of 3. So I can have that 3 there, times it by the 2n to the 5th, 2 to the n plus 5. Now I'm going to go ahead and divide each one of these terms by 2 to the n. And so I come up with 2 plus 5 over 2 to the n. 3 times it by 1 plus 5 over 2 to the n. As n approaches infinity, of course this term here is going to go to 0, this term here is going to go to 0, and I'm going to come out with 2/3. So notice that it is less than 1, therefore I know that this infinite series here absolutely converges. Now let's go ahead and take a look at a particular example where it diverges. If I have the 2n factorial divided by n factorial. Notice again, here is the a to the n plus 1 term, times it by the reciprocal of the a to the nth term. And notice that we're going to come out with a lot of cancellations. So what we're left in the denominator is just the n plus 1 times by the n plus 1. Now be careful with this one. This is actually 2n plus 2. And this is just 2n factorial, so that means that what we're left with is a 2n plus 2 and a 2n plus 1 factors. So if we go ahead and take a look at our cancellations, so I can factor out a 2 here to come up with an n plus 1. And so one of those will cancel, and I'm coming out with 2 times it by 2n plus 1 divided by n plus 1. Of course, if we take the limit as n approaches infinity, that's going to be equal to 4. So we know that this particular infinite series is divergent. Now, let's go ahead and take a look at a situation where the ratio test is inconclusive because we come up with a result of 1. So I have 4 to the n factorial divided by the quantity 2n factorial. And again, here's the a sub n plus 1th term, and this is the a sub n term reciprocated. And so I come up with all kinds of cancellations. And what I'm left with is 4 times by n plus 1, divided by 2 times by n plus 1, times by 2n plus 1. And so I'm coming out with then 2 times by n plus 1 divided by 2n plus 1. So what I'm coming out with then, if I take the limit as n approaches infinity of this particular absolute value here, I come up with a value of 1, and so therefore it's inconclusive, and I need to go ahead and take a look at other means by which we can go ahead and determine the convergence or divergence of that particular infinite series. Now, the thing that we're going to also have to take a look at, and I'm hoping that you recognize through these examples that we looked at, is that it's very useful to use with series with exponentials and factorials. Because of course the exponentials and the factorials will cancel each other out with the ratio test. And so there you go. With the ratio test again, we're using it to determine if a series is absolutely convergent or not. We're comparing it to the value of 1. So if it's less than 1, absolutely convergent. Greater than 1, divergent. Equal to 1, inconclusive. And it's going to be a very nice means to test for convergence or divergence, because we don't need to search for another particular series, and it's going to be particularly useful with series with exponentials and factorials. So we'll go ahead and work with the ratio test in class as well, and see if we can go ahead and make sure to use this properly to determine the convergence or divergence of infinite series. See you later. Bye-bye.